my pleasure to introduce our next speaker, Thomas Koopman, who's talking about rank-polymorphism for shape-guided blocking.
Yeah, thank you. So this presentation is going to be all about matrix multiplication. And as I'm sure most of you are aware, there are a lot of optimized libraries. So here's a small excerpt from BLAS, which is a library optimized for CPUs. And it's a great library, it performs very fast, but as you can see, the code is not particularly readable. And as we are at ICFP, I'm sure you all care about the specification of the program as well as the quality of the generated binary. So it would be great if we could have a specification like this, which actually performs as well as a optimized BLAS implementation. So in this presentation, we will try to convince you that it is possible to generate something that performs well from a specification like this, that is also good for formal reasoning and functional programming. So as any presentation about matrix multiply, some of you are probably wondering, who cares? It's already a solved problem, there's a lot of research in this. But there are still, to an extent it's true, there are already good libraries, but there are still some cases where you might want something like this. For example, if you're very paranoid. These BLAS libraries have been well tested, but they are very large, they use a lot of techniques, and it is not obvious for the programmer that this works. So it would be nice if we have a small mathematical specification that we can prove actually gives the correct answer. Secondly, we are here to convince the high-performance community that functional programming is feasible for high-performance computing. So then it is not a weakness but a strength that we can point to such a well-known example and show that we can generate something good from it. And finally, I also find it a very instructive example because you can very easily change strategies, see how it works, and that way also gain some insight in how a high-performance matrix multiplication works. So the goals that we have is to find a concise high-level specification of the algorithm and generate a high-performance binary from it, and also do it in such a way that we can reason mechanically about this and actually prove using, in our case, ACDA, that this strategy leads to a correct specification. So kind of what the previous speaker said no one cared about. So the way we are going to do this is to first talk a little bit about the key idea behind any high-performance matrix multiplication, which is to formulate it recursively. And then we are going to develop a model for this in ACDA and prove that this idea, so it's called blocking usually in the literature, actually works. So here I have the mathematical definition of matrix multiplication at the top. So it takes two two-dimensional arrays A and B, and it returns another two-dimensional array. At position ij, it's equal to the inner product of the ith row of A and the jth column of B. And below there is an implementation in a functional array broken in Lang's SAC, which we use to get the actual implementation. So as you can see, it's pretty close to the mathematical specification. So here we see the performance, and on the y-axis we have the performance in gigaflops, and on the x-axis we have the threads we use in the multi-threaded implementation. And you can see we have perfect linear scaling, which is pretty suspicious. And indeed, we only get about 1% of the peak performance of our machine, which is about 1500 gigaflops. So what we need to do is we need to improve the cache behavior. So if you just take the naive implementation, then you get about one floating point operation per element. So what you need to do is you need to decompose the matrix multiply in smaller parts so that we get a higher intensity per flop. So here's an excerpt from the seminal paper on this from GoTo. And as you can see, we block matrices into smaller block matrices. And that is basically the idea behind any high-performance implementation. And this is pretty high level and mathematical. So this already tells us that maybe it's not necessary to go into all the low-level details and assembly that libraries do. So here's a concrete example. We have a 4x4 matrix of scalars, but we can also interpret this as a 2x2 matrix whose elements are again matrices. So I have one slide for the people who are into math and kind of annoyed that we just randomly add structure here. If you don't care, you can ignore the next minute. So matrix multiply is really a composition of linear maps. We have some basis elements and then we return a coordinate vector. So what we do by blocking is that we just decompose the domain and codomain in direct sums. And then we can specify our linear maps in maps between these elements. So here we have, we decompose the four-dimensional domain into subdomains which are each two-dimensional. And well, that is basically the mathematical intuition behind it. So if you program it, it kind of looks like this. We still have a sum, but instead of the multiplication of scalars, we have a multiplication of matrices. So if A and B are here four-dimensional matrices, then the elements are two-dimensional matrices, and we can do our normal matrix multiplying this. So here's an example implementation in SAC, which shows this for one level. But as you can imagine, this may become quite annoying soon because we have, well, the registers as a level of memory we might want to do this for, but also L1, L2, L3. Maybe we have a distributed system with multiple nodes. So it would be nice if we didn't have to write 10 of these. And so have some kind of arbitrary recursion. So that is where the title of this talk and paper comes in, the rank-polymorphism. To specify this elegantly, we need to have a notion of generally of arrays of general dimension, so rank-polymorphism. So that's what you see here. The plus is really any number of dimensions that come after it, and the only thing we ask is that the first two dimensions line up, and then we can do this recursion on the shape until we have scalars, and then it's just normal multiplication. And this way we can encode the entire strategy of our blocking into the shape of the arrays. So we can have the slow and the fast version with the same specification, and the shape of the matrices determine how it will actually be executed. So here we see the performance of this. That is the red line compared to the black line of the Neve implementation, and as you can see, it's about 100 times faster. The y-axis is log scaled, and we can see that we are actually competitive to state-of-the-art implementations such as OpenBLAS and MKO. So I should say it is code generated like what I showed you, but not exactly the same, because we still have some problems in our toolchain. You can see the paper for details, but in short, GCC does something weird with the code. So we wrote our own C program. It doesn't use anything weird or inline assembly. It's only 40 lines. So we expect that future implementations of C compilers will be able to handle this. And also our SAC compiler copies out blocks of memory if you specify it like we just showed, so we also have to tweak it a little bit there. So now we show how we can get the performance, and Artjoms will now tell you how we can show this is correct using Octa.
Thank you. Yeah, indeed. So, in some sense, I think that the story can be seen that I'm going to present the first letter of the acronym of the workshop that we are at. So you saw the three letters, and this is exactly the discussion that we had on our Slack channel when we were writing this paper. So these guys said, we need performance, and I said, are you sure that we're doing actually the right thing? Are you sure that we're computing the same thing? And sometimes we didn't. I remember one case that we had a fantastic speed up, but the results were all wrong, right? So because we failed to just multiply something. Anyway, so we want to use dependent types here to make sure the specification is correct. And with dependent types, it's always the same problem. Which representation do you choose for the problem to make sure that your proofs do not turn into a nightmare, right? And so it turns out, so the key slide of the specification that we came up with is this array theory. So what it consists of? Well, I'm going to use Agda through the slides. Don't read the code too much. It has been type checked, I promise you. I made sure it is. Just follow the general gist. If you're completely lost, please stop me. I'll explain you what happens here. So, as in many array languages, we say that arrays are functions, right? Arrays are just functions from indices to values, and this is given by this type here. So S is a shape, and PS is the positions that are given by this shape, and this is our array. That many array languages do this. And then the key question is, what is the shape and what are the indices that this shape, the index space that this shape gives? And the key idea that makes this entire development very beautiful is that we treat our shapes as trees of natural numbers, binary trees, not lists, but trees. And this gives us a very necessary induction principle that we need to have in order to prove the blocking. So shape has two constructors, the singleton and the product, and the leaves of the trees are natural numbers, and then you have an operator to compose two trees together. And then the index of shape S says that the index is exactly the same tree as shape, but all the leaves are element-wise less than the corresponding leaf in the shape, right? So you can imagine that you have the same situation with lists, but you just compose this lists with append rather than with cons and tail, right? So why is this useful? So let's just build up these combinators that we need in order to specify and prove the blocked version of matrix multiplication. So the functions immediately give us ways to construct and destruct arrays. So as arrays are functions, you use lambda to construct an array and use application to select from array. And we give it a bit of a nicer syntax with these square brackets here. But it's just the application. What is more interesting is that this product in the shapes gives us the ability to switch, to view our arrays of a product shape as nested arrays, right? So our arrays are very regular. They're just rectangles. Therefore, the product shape can be split into an array of arrays. It's not a general property of arbitrary container because it's not guaranteed, but as our arrays are in a sense very simple structure, you can do this, and this really corresponds to some kind of currying or I don't know, monadic join if you want, but it's just very useful. In this encoding, all the elements, so all the accesses to the elements, they don't have any dependency. So it's, the container just has a bunch of elements hanging in, and all the accesses are independent. So therefore it's a functor and it's an applicative functor. Therefore you have all the applicative operators immediately given to you, right? So you have a constant array given by k, you have a map given by composition, and you have zip width just given by the same function application. And now, in order to state something about being the same, so one algorithm being the same to the other algorithm, I'm introducing the equality relation, which is just the element-wise equality. So when I talk about that, when two arrays are the same or two algorithms are the same, it means that they compute the same elements. So we're not on a typing conference, right? So I don't have to talk very carefully about equality, which is a very good way to start a violent fight, right? So I'm just saying that, you know, extensional equality is all I have. I don't care about high equality. I don't care about automorphism. So just compare the elements. If they're the same, I'm good. Now, the naive matrix multiplication in this system is specified like this. So you can see that we can encode the necessary matrix multiply relation so that this subshape matches as follows. And all we have to do is do the sum with plus over, well, aik times bkj for some chosen multiplication-like operation, zero-like operation, plus-like operation, and sum, which is it's a multi-dimensional version of fold. So you fold all the elements of the array using this binary operation and this neutral element, right? Just choose your favorite implementation, and this is going to be your matrix multiply, the naive one. Now, the key feature of this specification is it's rank polymorphic, right? I mean, I feel a bit silly that I keep repeating this rank polymorphic, like, you know, one-trick pony. But this is a very good trick, right? And the point here is that it's rank polymorphic because this subcomponents S, P, and Q, they don't necessarily have to be of rank 1, right? So it's not really two-dimensional arrays. These are arbitrarily dimensional arrays, which you can split into these subparts, right? So they can be 5,000 by 3,000 dimensional things, right? Specified like this, right? And this is very useful. Why? Because we're going to derive the blocked algorithm from the original one, but we have to talk about what the blocking means, what the blocking is in this system. So what is the blocking is? What is the key feature of blocking? The key feature of blocking is that you want to turn an array into an array of arrays, but you want to preserve as much as possible the local neighborhood of the elements, right? So if if in the original array you had some elements close together by some proximity matrix, then the blocks that you get has the same proximity matrix as the original array. So in this system, we consider three cases. So when we block about, again, hypothetical rows and columns, once again, this is rank polymorphic in the sense that these things are not necessarily of rank 4. It can be arbitrarily, given that you can split them this way. And if you want to block across both rows and columns, then you take this 4-dimensional thing and you move P and R together into a block, right? And as an action on indices, you simply swap these middle things around, right? That's all what blocking does. So it's really, if you want to express the blocking, you take the element, you reshuffle the components of the index that you select at, and you've blocked your array. So it's quite straightforward. It has immediate inverse, which is itself, because you just rename the variables, and if you swap the index twice, you get the same index back. Right? So that's pretty straightforward. If you want to block across the columns, I call it vertical blocking, then all you do, again, you just move this component of the index to the front. You just swap them around, and again, it's just a self-inverse. If you block on the rows, you actually have to change the association of the parentheses, right? So you go from SPQ to SPQ with parentheses swapped, and there you have to do a bit more work. But again, it's not a self-inverse, but it's a pretty straightforward expression that you can immediately write. Okay. And this is all. Again, don't read too much of the code, but this is going to be the general structure of our blocked matrix multiplication. So what do? We start with exactly the same signature, and then we just consider all the cases that S, P, and Q, the subcomponents of the shape subcomponents, can consist of. And every S, P, and Q can only consist of either a single, it can only be either a singleton, this iota, or a product itself. And if we consider all the 8 possibilities, then we implemented the blocked matrix multiply for all the possible shapes that you can come up with, given that these relation holds. Now, what is the strategy? So if you give me actually a matrices of rank 2, I'm going to apply this naive canonical matrix multiplication. And now, if you're going to have anywhere any further component, any further subcomponent is a product itself, then all I'm going to do, I'm going to reshuffle the shape components in such a way that I can make a recursive application. And the nice story about this particular formulation is that, in a way, you almost get it by brute forcing. It doesn't read like this, but if you try to write it, you don't have a lot of moves to make in order to reshuffle your data such that you can make actually the recursive call, right? And if you consider all of them, you get the matrix multiplication, the block matrix multiplication. Okay. Now, it's all good, but it's not obvious that this is correct, because you go and you start shuffling things around and you reapply recursive things to subparts, which is always a bit scary and suspicious. So, how do we prove this? What do we need to prove that this is correct? Actually, not much at all. So here, I just specify a sensible fold for multidimensional array that folds the elements bottom up. So first it folds all the one-dimensional things, then it reduces the rank to one less, it folds further till it gets to a single element X, right? Again, the details are not that important, but it's the very naive version of the fold that you can come up with. And if you do this, then showing that the blocked matrix multiply and the naive one is straightforward. You just need one lemma that tells something about the way you sum elements around. Now, what is interesting about this particular result is that I can prove that this blocked matrix multiply on the very generic types. By the way, you see that these X, Y, and Z are all different types. They might be at least all different types. And I do something with the kind of the order that I do the summation, but I never require any properties of these operations, right? So this operation, this block matrix multiply, computes the same result for arbitrary multiplication 0 and plus that you choose, which is interesting. Now, why this is the case? This is the case because the blocking that I defined here never changes the rank of the array, right? It only transposes certain things around. So it reshuffles the index components, and then it reshuffles them back when it's done applying things recursively. So I never reduce or increase the ranks of my arrays. That's why this result. So if you've chosen the decomposition of your matrices into subblocks, then this thing is almost trivially or very simply computes the same results as the other one. Now, if you actually want to compare the matrix multiplication on the truly two-dimensional array, or array of rank 2, and the blocked matrix multiplication where you have a larger shape, then we'll have to require certain properties like associativity and neutrality of the neutral element. And then basically all that is going to be needed is this operation that can turn a shape into a flat shape. So you can always compute the number of elements in your array by just following the structure, and then you can turn always a shape into a singleton shape by squashing all the elements, and you can do it in both positions of the matrix, and then you can have functions that translate back and forth. Okay, and then you can show that it still is fine. Now. The slides that Thomas showed before with the SAC version, it only had 2 recursive cases, right? But my version had 8. So what's the difference? The difference is that in SAC, shapes are more like lists rather than trees. Therefore, it's very easy to make the shape recursion go left to right or right to left, right? And therefore, if we want to emulate what happens in SAC in this system, we have to make sure that the shapes that these matrices have, they adhere to a certain property, which means that the tree is kind of left-nested or right-nested, and preserves the necessary matrix multiply relation that you need to compute to matrix. Well, that the matrix multiply has. And if you do this, so again, it doesn't matter what it's written here, but this is this relation that makes sure that the shape tree is left-nested. And then if you have this witness, then you can indeed reduce to the SAC version that basically has only 2 cases, right? And it's going to do it's going to always do the blocking on both rows and columns. I think that's pretty much it. So what did we learn? So we have a rank-polymorphic array theory. Again, on the slides, it might be not theory; it's initial model, but we can make it more generic. And I think the key point here is that it's so minimalistic that it's almost like funny, right? So we spent ages and ages to developing the array languages, and in some sense what we actually need to do is blocking fits in 6 lines of AGDA code, right? Which is quite beautiful. So this theory gives us the necessary power to express blocking. We also can prove correctness, and actually, if you look closely at the AGDA code and SAC code, then the difference is not that great, right? So, which means that currently we translated the AGDA code into SAC code manually, but it's very plausible that we can automate this process because the difference is not that high. We need to throw most of the typing information, and then basically we can get the SAC code out of AGDA code quite easily. And I think that's it. Thanks very much.
Thank you. I thought
Not really, because there's definitely a possibility. So all you need to do is, as I'm doing here, right? You'd have to introduce extra relation to say that the shape is actually 2 to the power of n unfolding. So this is a bit more general than you need for specify the stretch algorithm. But you can always fix this by saying, okay, I know something more about my shape. So specifying this is not a problem. The question is whether you really want to do this. If you read the high-performance papers, then there's a mixed feeling about the stretch algorithm. It's definitely possible, but so technically, yes. We didn't play with this because our goal was first to just catch up with the Goto paper, and the Goto paper just does this, right? It just blocks by carefully choosing the sizes based on the registers, caches, and threads.
So when you move between flat matrices and your first blocking step, then you need associativity of addition. And one of the things you might find in matrices is floating point numbers, for which addition is not associative. So what's the story on that? Is it just floating point matrices are out of scope, or is there something more one can say?
Well, this is not a problem of this system, right? so I don't know. I mean, I think realistically most of the high performance matrix multiply libraries don't care about this. They silently switch on unsafe math underneath, and then you have to live with the fact that it's the addition and multiplication are not associative in IEEE, right? I mean, what can you do? Well, I mean, I don't know. You can surely, if you really care about correctness, you can show to arbitrary precision floating point numbers, but then you lose performance, obviously, right? I mean, but I don't think that this is a help of a model or a compiler, right? This is a decision that, in a way, you have to take. What do you want, right?
So is correctness of this algorithm important if you are in any case going to say, well, you know, but the assumptions are not fulfilled in reality?
Yeah, well, the correctness of this algorithm is not intact because you won't be able to prove the associativity of your floating point addition if you use IEEE, right? Yeah. So, but I mean, this is not the problem of the algorithm, it's the problem of the underlying medium, right, in a way.
So like a two-directional question. So what would go wrong? Would anything go wrong in the Agda part if at the very beginning when you define shapes and positions, you already have lists instead of trees. So like the base case would just be nil, like a scalar case rather than a finite array case. And then the inductive case, even like the very first, I think the very first Agda slide you had, like even before you do blocking, even before matrix multiplication, when you're just define, even like here, right? Suppose that the two cases are like a unit case and a cons case, right? A cons case where you take a, so you
can define list. You can define list.
Yeah,
yes,
list, and then the positions just so would anything go wrong with the rest of the development?
Oh, nothing will go wrong. It's just these proofs formulating this algorithm of blocked matrix multiply is going to be much harder because you will have to constantly transport along the append. So append is not going to be a constructor. Append is going to be a defined function, and therefore you say, "Oh, I know that I can split," but actually, when you apply, you always think in terms of constructors, right? But you now have, express the algorithm in terms of the function that you define on these constructors. So you'd have to constantly transport back and forth, and there's a place called transport hell, and you don't want to be there.
So it's not just about permuting the first three elements of the list. You actually have to have append. Like
yes, because this gives you the ability to split anywhere in your shape vector.
Right. The other direction is like, what would go wrong in SAC if you just had trees?
You have to implement them efficiently, and that's actually what we've been thinking about. But again, SAC is what 500,000 lines of C code, and it's already very non-trivial to do what we have. So and this is a major change. So in theory, it's perfectly possible. It's just how do you make sure that the shape descriptors that you carry around potentially at runtime are efficient in decoding the tree structure and putting it back, right? That's really the only question that you have to answer. If you can do this efficiently, and I think in principle you can, you're fine. But we never tried. Maybe there are other problems expecting us around the corner somewhere.
So actually the question about Strassen and the floating points made me think about a question for future work. So in numerical computing, people most of the time don't care about actual equality as long as the computation is numerically stable, which is I think also the reason that Strassen isn't really used in practice. So maybe if you want something like this, you have to formulate numerical data instead of equality. And see, that way you can still kind of square the circle here for the correctness part.
I do have one question.
Yeah.
You mentioned that when blocking, you have to be careful to leave basically elements which are in the original matrix next to each other, close to each other. But I didn't get completely why that is important, because if you look at a matrix, you have a flat layout in memory as well. So
that's what you assume.
Yeah.
Well, this system doesn't assume anything in
But
about memory, right?
what do you, so is it what do you get, what, I might have missed that, maybe you mentioned it, but what are you losing if you lose that restriction or give up on that restriction?
You lose, well, in performance, exactly, you're going to lose the continuity of your elements in memory, right?
So that you basically assume that, or want that something that's programmed originally with the assumption that there's good locality between elements which are kind of neighboring in the actual abstract matrix. Also, the locality.
There are two things. So first one is, yes, this performance-wise is this, yes, but also just mathematically, you have to, the blocked algorithm works only if you do the blocking this way. I was just trying to motivate what the blocking means, right? So I mean, if you look at in the literature, what the blocked matrix is something like this. But so I was just trying to explain.
Oh, okay.
Yeah,
yeah.
So.
Okay, thank you. Do you have any other questions? Then thanks again, Artjom and Thomas.